Okay, so now we're going to talk about dimension of a vector space. So let V be a vector space, and suppose that B is a basis for V, and so we enumerate the vectors in the basis in B, in the basis B as B1, B2, Bn. Okay, so the following facts are useful for us before we actually define the dimension of V. So any set of vectors, so the first fact is any set of vectors that contain more than n vectors in V must be linearly dependent. So why is that? So suppose that we got p vectors, v1 through vp, where p is bigger than n. Right? So these are the vectors in V, and so how do we tell that this set of vectors must be linearly dependent? So one way of doing that is we look at the matrix whose columns are the coordinates of vi's relative to the basis B. So v1 sub B is the first column, v2 sub B is the second column, vp sub B is the last column of this matrix. Okay, so note that this matrix is an n by p matrix, right? Because it got p columns, v1 sub B up to vp sub B. Each of the columns is a vector in Rn, right? Because remember, v1 sub B is the coordinates of v1 relative to the basis B, and B has n vectors, so this is a vector in Rn. So it's got p columns and n rows, so that's an n by p matrix, and p is bigger than n, and so this matrix got more columns than rows, right? So it cannot have a pivot in every column, right? Because it got more columns than rows. So we know from before that if you got a matrix that cannot have a pivot in every column, then the columns of the matrix cannot be linearly independent, and so the columns have to be linearly dependent. And so this gives us that the original vectors v1 through vp must be linearly dependent, right? Because remember, we from the previous lecture we talked about the idea that the coordinate map preserves all linear relations between vectors in V and the vectors in and their coordinates in Rn. So whatever happens, whatever the relations between the coordinates of those vectors in Rn, the same relations must hold for the original vectors. Okay, so that was the important idea that we've used various times already, and so here it is used again in this setting. And the second observation is that every basis of V must consist of exactly n vectors. So B has n vectors and it's given to be a basis for V, right? So why is it that any other basis has to have exactly n vectors? So let's say B1 is a basis of n vectors, right? So it could be B, and B2 be any other basis. And let's say the size of B2, the number of vectors of B2 is k, right? So it's just some number. While B2 is linearly independent because it's a basis, and so by fact 1, the number of vectors in B2 must be at most n. So k is less than or equal to n, right? Because otherwise k would be bigger than n, and fact 1 would tell you that B2 must be linearly dependent, and it's not because it's a basis, right? On the other hand, we do the same argument. So B2 is a basis of size k, and B1 is linearly independent. So again, by fact 1, the size of B1 must be at most k. So n is less than or equal to k. So we got k is less than or equal to n, and n is less than or equal to k, so in fact they must be the same. And it turns out that fact 2, namely every basis must have the same number of vectors, holds for infinite dimensional vector spaces also, but we're not going to go into that. Okay, so now we're going to talk about dimension of a vector space. So the definition, so from the previous slides, we know that if you got a vector space, any basis of that vector space has to have the same size. And so we define the dimension of vector space V as the size of some, or equivalently any basis of V. If a basis has only finitely many vectors, then we say that V is finite dimensional. If a basis has infinitely many vectors, then we say that V is infinite dimensional. All right, so now let's look at various examples of vector spaces. So if you are in a vector space V, there's always the zero vector, right? So take the set that contains only the zero vector, so it's going to be the singleton zero vector there. And this is kind of a special vector space. It is the only zero-dimensional vector space. In other words, it's the only vector space without a basis, right? So just the zero vector there. So nothing in this set can be a basis. So that's why it's called the zero-dimensional vector space, because it's got a basis of size 0. In other words, it has no basis. Okay, other than the zero vector, if you take any non-zero vector, call it V, look at the span of V, then that's a one-dimensional vector space, and a basis for that is V, right? Just a one size 1 basis. More generally, if you take if you have k vectors v1 through vk that are linearly independent, then the span of v1 through vk is a k-dimensional vector space, and a basis for this vector space is the set of vectors v1 through vk. So generally, Rn is finite dimensional and has dimension n. P sub n, the polynomials of degree at most n, is also finite dimensional and has dimension n plus 1. Right? So just for example, the vector space that we used in the previous slide or in the previous lecture was P sub 2, and that's a vector space of dimension 3, and a basis for that, a standard basis for that, is the set of 3 vectors 1, x, x squared. And so in general, if you have P sub n, then a standard basis for P sub n would be the vectors 1, x, x squared, up to x to the n. So that set has n plus 1 vectors. On the other hand, there are vector spaces that are infinite dimensional. So for instance, P, the set of all polynomials, is an infinite dimensional vector space. The set of all functions from R to R are also is also infinite dimensional. All right, so let's talk about subspaces. So we have defined a subspace before. So if H is a subspace of a vector space V, then it's just a set of vectors in V that has 3 properties, right? We call that H has to contain the zero vector, H has to be closed under vector additions, and it has to be closed under scalar multiplications. Okay, so if H is a subspace of V, then the dimension of H is at most the dimension of V. So that's fairly obvious. So if V is a finite dimensional vector space, H is a subspace of V, let's say it's a strict subspace, so it's not the same as all of V, then in fact the dimension of H has to be strictly less than the dimension of V. And curiously, we're not going to go too much into this, but this is actually not true for infinite dimensional vector spaces. And so for infinite dimensional vector spaces like the P vector space of all polynomials, you can find strict subspaces of H of P such that the dimension of H is the same as the dimension of V. Okay. For finite dimensional vector space V, then we also have the following fact that was observed before. Any linearly independent set of size n is a basis, and the same is true for any spanning set of size n. And the point is just that if you got a linearly independent set, you can extend it to a basis. And if you got any spanning set, you can take off vectors until you got a linearly independent set, until you got a basis. Okay, so this is sort of what we did before. So let's look at an example. Okay, this is an example of how to determine the dimension of a subspace of a vector space. So in this case, we look at a subspace H of R4, and H is given to consist of vectors in R4 of the form, the first coordinate is A minus B plus C, and then the second one is A plus D, third one is 2B minus 2C, and the fourth one is 3D, where A, B, C, D are any arbitrary real numbers. Okay, so how do we determine the dimension of H? So first of all, make the following observation. So take a vector in H. So say X is the vector A minus B plus C, A plus D, 2B minus 2C, and 3D. It is fairly clear that you can express X as a linear combination of the following four vectors: 1, 1, 0, 0, minus 1, 0, 2, 0, 1, 0, minus 2, 0, 0, 1, 0, 3, right? Because you can just group, this is the trick that we've done several times before. Like, for instance, in the calculations that isolate bases for null space of a matrix, right? So you write X as A times 1, 1, 0, 0. So the idea is that you split X into the part that only consists of A. And so in this case, you have A times 1, 1, 0, 0. So that's the part that consists of only the terms with A. And then now you do the same for B. So this is going to be B times minus 1, 0, 2, 0, and then C times 1, 0, minus 2, 0, and D times 0, 1, 0, 3. And so let's call those vectors V1, V2, V3, V4. Well, clearly the span of V1, V2, V3, V4 is all of H, right? Because any X is a linear combination of these four vectors. So that tells us that you got a set of four vectors that spans all of H. So dimension of H has to be at most 4, right? So could it be 4, or could it be smaller than 4? Well, we need to find out whether the V1, V2, V3, V4 is actually a basis for H or not, right? So the thing to check is that we need to check that these vectors are linearly independent, right? So how do we do that? Well, this is fairly standard by now, I hope. So you put these vectors into a matrix, right? These are going to be the columns of this matrix A. So 1, 1, 0, 0 is V1, minus 1, 0, 2, 0 is V2, 1, 0 minus 2, 0 is B3, and B4 is 0, 1, 0, 3. Row reduce this matrix to its row echelon form, and so you should do this, right? And what you see when you do the row reduction is that the second column is without a pivot, and the other three columns will have a pivot. And depending on how you do this, but maybe you could, some of you may find that the third column doesn't have a pivot or something like this. That's fine. But the point is that one of the columns, so in this case the second or the third column, will not have a pivot, and the other three columns will have a pivot. So that tells you two things. It tells you that the vectors are linearly dependent because not every column has a pivot, right? So we've done this. And more importantly, the second thing it gives you is that because the second column doesn't have a pivot, you can throw it out. And the other three columns, V1, V4, and V3, have pivots, so that actually forms your basis there for the column space of A. So the conclusion is that the dimension of H has to be 3. So we're done. So lastly, this is just a review on the column space, row space, null space, and the dimension. So we've done this before, so I'm just sort of recapping the important points about these concepts. Nothing new here. So let's say A is an m by n matrix, and so the relevant definitions are the column space of A, the row space of A, and the null space of A. So you should recall these, right? The column space of A, by definition, is just linear combinations, the spans of the columns of A. Row space is the span of the rows of A, and null space is the set of all x such that A times x equals 0. So the set of all solutions to the homogeneous equation AX equals 0. Now, if we row reduce A to a row echelon form B, then we note that the row space of A is equal to the row space of B. And I explained this in class before, but broadly speaking, since you do row operations on the row, so every time you do row operation, you simply don't change the row space at all, because you just turn a bunch of rows into their linear combinations, and so then the row spaces don't change, and the fact that the row operations are reversible also tells you that. Okay. And so when you row reduce A to its row echelon form B, you see that some rows of B have pivot and some don't, maybe. Take the pivot rows of B, and that's going to be a basis for row space of A, right? Because the row space of A and row space of B are the same, and the pivot rows of B will form a basis. Slightly different for the basis for column space, right? So remember, the row operations do change the column space of the matrices. So in general, the column space of A is different from the column space of B, but the linear dependency between the columns don't change as we do row operations. So we look at the pivot columns of B. These will give a basis for the column space of B. It doesn't quite give a basis for column space of A, but you can go back and pick the corresponding columns of A, and those will be a basis for the column space of A. Okay, so that tells you how to compute rank of A. In other words, the dimension of the column space of A. Right, so to find the dimension of the null space of A, or nullity of A, we count the number of free variables, i.e. the number of columns without a pivot. And and we did this many times, and so you can go back and work out the examples that I've done in class, or the examples in the book, about how to compute the dimension of the null space of A, as well as computing a basis for the null space of A. And lastly, the rank nullity theorem says that if you add up the rank and the nullity of the matrix A, then you get the number of columns in. And as we said before, it's very easy to remember this theorem. The rank of A is simply the number of pivot columns of A, and the nullity of A is the number of columns without pivot of A. And so, of course, when you add them up, you get all the columns, right? So that's it.